Okay, um, I'm going to do this tutorial. Okay, it's a pre-recorded session, but something to encourage you. Applied is not really difficult, but if you are not following what um you have been taught, you are going to mess up big time. Right? That is very easy. So in this tutorial, we are going to try and solve questions in applied electricity. This is just going to quicken you up because you've already learned and you know so much. You know so much. This is just a recap of what you've done, right? But pointing out mistakes that students usually make so that you don't make similar mistakes, right? So this is to help you um, perfect what you've already learned. And if you have to revise, some concepts will be made clearer in this tutorial. Okay. So I'm going to start with single phase AC circuits. Mostly for this one, it's going to be all in words, no circuits. If you are going to draw a circuit, then you would have to use your own imagination to draw them from the question, right? But AC circuits are basically very simple. For me, I advise most students if the exam is in order, like it starts from DC, then it comes to AC, comes to three phase, and it comes to magnetic circuits. I would prefer you go and start with your AC and finish it easily because it's very cheap, right? Finish it quickly because it's very cheap. Then you can have you can have more time to do your magnetic circuit and your DC part. All right. So we start um with this question. It says a delta connected motor is connected to a 4000 volt three phase 50 hertz line. The motor produces an output power of 2900 kilowatts at an efficiency of 95%, a power factor of 0.9 lagging. Good, right? So let's see, they've given us our V. The motor is delta connected, right? So you're looking at something like this. There's a load here, there's another load, and there's a load here, right? So I'll start out with pointing out certain things in um, single phase machines like this. If you have a single phase balanced load, right? Um, we know phase voltage is line voltage over root 3. For delta, sorry, for delta, we have our phase voltage to be equal to our line voltage, our phase current to be equal to our line current over root 3, and then the same S is equal to VL IL, right? These are the formulas you should note. When you are looking at a star connected load, when you have a star connected load, you realize your phase current is equal to your line current, your phase voltage is equal to your line voltage over root 3, and S is still VL IL, right? All right. So let's get jump back to this question. So the motor produces an output power of 2. So this time they've given us P out to be 2900 kilowatts, right? And they've given us efficiency to be 95%. That's 0.95, right? And power factor to be 0.9 lagging. right? The first question is calculate the active power absorbed by the motor, right? So what happens is you have your motor here is producing some power, but before that you have to supply some. So you supply power to the motor and it produces some power at the output. So they've given us the output N to be 2900 kilowatts. We are looking for the input, right? And they've given us the efficiency. So in SHS, we learned something about efficiency, that not all machines can convert 100% input of their power to the output, because there's going to be some form of losses in the machine. So we know that our efficiency is equal to output over input, right? So it means we can manipulate and make input the subject so that we have it to be output over our efficiency. So according to this question, our input power, right? Input power, active power, P. We know active power is P, or active power is the same as true power. Active power is the same as just power, like power, not quantity power. Okay, so we have um, our output 2900 kilowatts divided by 0.9. Sorry, it's 95, right? 0.95. So if you do that computation, you are going to have 29. You are going to have 3052.6 kilowatts. Good. That's our input power. Input active power. The next question is the reactive power absorbed by the motor, right? Reactive power is what? Q. So Q of the motor, right? Don't find Q of the motor. But before we find P, before you find Q, there's a relation between P and S. We know that P is equal to S cos theta, where cos theta is what? The power factor. So it means we can find S from this. So we can say S is equal to P over cos theta. Our P was what? 352.6 kilowatts divided by cos theta. Cos theta in this case is what? 0.9. Right? It means our S, where S is what? Apparent power, right? It's going to give us 339.8, right? And this one is going to be in kVA. Okay. Now that we found P and S, we know the relation between P, P square plus Q square is equal to S square. So we can find Q to be root of S square minus P square. That's going to give us Q. So 391.8 square minus 3052.6 square. And this is going to give us 1478.52, but it's going to be in what? kVAR. That's our Q. So you solve the question, you solve the I, and we solve this. Then the next question is find the motor line current, right? Motor line current. The relation between the motor line current is S is equal to what? VL I L. This is the line current, this is the line voltage, and this is the apparent power, right? So we know S was giving us to be 3391.8, right? Divided by is equal to the line voltage was also given to be 4500 volts. Please take note, mostly unless it is mentioned that it's phase voltage, all voltages given are line voltages, right? Even if it's not mentioned that is the line voltage, is the line voltage. We always give values in line values unless it's stated clearly that is a phase voltage or phase current. Know that what they are giving you is a line current. Okay, so it's going to be 4500 IL. So at the end of the day, IL is going to be 3391.8 divided by 4500. That's going to be 0.75 amperes, right? So that's the solution to that question. That's how we solve a question of that nature. So someone would ask, right? The reason, remember we said for delta connected, your phase voltage is equal to your phase, the line voltage. If it were star, then in our case, we would not use, okay, so it was already given, but be careful when you are changing, especially for phase voltage and line voltage. I think something like that will pop up and I will get to explain it. All right, so let's go with the next question. Let me delete this. Okay, for the next question, definitely you are going to get a question like this. It comes mostly, right, where they give you loads and you have to find the apparent power, the total power factor, the there are loads in parallel and you have to find their combined power factor. You have to find their combined apparent power. You have to find their combined true power. You have to find their combined reactive power, right? Because when you come into your house, there's a fan, there's a light bulb, there's a fridge, there's a motor, there's a blender. All of them consume power in a certain way. So if you want to know the whole house, how much power are you consuming? How much apparent power are you consuming? How much real power or active power are you consuming? How much reactive power are you consuming? And what's the total power factor, right? Because every device will consume different um, power at different power factors. So we want to look at that. So for this type of a question, it's easy if you can draw this table, right? It's just a short table that will help us solve it quickly, like fast, 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 fast. Right? Okay. So the first part of the table is just going to be the loads we are looking at, right? Then the next we are going to say our K, our S in kVA, then cos theta, then our real power in kilowatts, then sine theta, and then the last part is going to be our Q in kVAR, right? Then with this, we are going to use that to solve our total load. The first load given is what? A fan with a motor, right? They are saying it has 4 kVA. It means they are giving us the S. So we have S, which is in 4 kVA. The power factor is 0.8. and it's lagging. I'll talk about this lagging very soon. Then the B is a 3000 watts radiator operating at unity power factor. Unity power factor means the power factor is 1, and the value was 3000, so I can say 3 kilowatts, right? So it means over here is going to be 3. How? So we filled in that information. Then the next load, right? This one is our radiator. The next load is uh, there's no name, but let's call it load 3, right? Has 2 kVA, 0.75 power factor leading. So let's write it 2 kVA, 0.75 power factor leading. Please take note of leading and lagging. I'll come back to it. Then the last one is a motor with output power and efficiency and 0.6 power factor leading. Just solve a question like that at the top. Right? They have given you the output of the motor, but what we need is the input of the motor. We are concerned with the input, so we have to find the input kilowatts, right? So for us to do that, we know that the input is just going to be the output over the efficiency. So that would be 1.8 divided by 0.8. And that's going to give us what? 2.25, but 2.25 kilowatts, right? Kilowatts. So 2.25 kilowatts. They have given us the power factor to be 0.6 leading. Good. Now to the leading and lagging. Sometimes you can be given a question where they are all lagging, right? Sometimes you can be given a question that it has a mixture of leading and lagging. Sometimes you are given just all leading and maybe a unity power factor, right? This is what you should know. And this is where it gets critical. Some people get confused here. If it's lagging, your Q value is going to be positive. If it's a leading power factor, your Q value is going to be a negative. So I'll just come here. I know my Q value for this one was lagging, so I'm going to have a positive value. This one is going to give me a negative value. This is going to give me a negative value. That's all. So we are going to start filling the table from here. So these formulas will help us. We already know them, right? We know them. The first one is, we know P is equal to S cos theta, or cos theta is just PF. Then we know, so I can come and say power factor is also equal to P over S, or I can say S is equal to P over power factor, right? And I also know Q is equal to S sine theta. To find theta, so sine theta is actually sine of the cos inverse of the power factor, right? Because we know cos theta is equal to power factor. Cos theta is equal to power factor. So I can say that theta is equal to cos inverse of the power factor. So these are what we are going to use to fill our table quickly. It's not a big deal, right? So a question like this, you should be able to score everything if you follow what we've done. So P is going to be this 4 times 0.8. So we are going to have 3.2 here. And sine theta is going to be what? 0.6. So you can do cos inverse of 0.8 to get your angle. Then you take sine of that, you get 0.6. So Q is also going to be what? S sine theta. That's what? 4 times 0.6. That's going to give me what? Positive 2.4. Then we just saw that we can find S by making P over power factor. So We have P, we have cos theta, which is power factor. So 3 over 1 is what? 3, right? If I do sine cos inverse of 1, I get 0. Sine 0 is 0, right? And P S sine theta, 3 times 0 is what? 0. Good. Then this load is going to be 2 times 0.75, which is 1.5 for P, right? Cos inverse of, so sine theta for that one is going to be 0.66. And if I want to find my Q, we've already seen that it's a leading power factor, so we are going to have a negative. So we are going to have negative 1.32, right? Then let's come back to the last load. The last load was the motor. We know P, we know cos theta. It means our S is going to be 2.5 over 0.6. 2.25 divided by 0.6. That would be what? 3.75. So if you want sine theta, it's going to be 0.8, right? That's, I take cos inverse of 0.6, then I take sine inverse of that, and I'll get 0.8. If I want my total Q, it's going to be minus, because it's a leading factor, leading power factor. Then we do 3.37, 3.75 times 0.8. That's going to give me 3. All right. But we spend time to do all of this, but at the end of the day, realize it's going to answer all of our questions for us, right? So the first one we were asked was find the total current, right? Find the total power, find the total kVA, find the total cost factor, and all of that is going to be from the question or the table we've drawn. All right. So let's find. So sometimes that's not all the parameters. So let's find all of the parameters. Our total Q can be found easily. Our total Q can be found easily from the table by summing all the components of Q. So it's going to be 2.4 minus 1.32 minus 3. That's going to give me minus 1.92. Then total P. From the table, we can only find total P and total Q by adding them directly, right? Aside P and Q, we use different methods to find total power factor and total apparent power. Please don't make that mistake of summing all the values of cost factor. Unfortunately, your answer will be inside, and that's wrong. If you also sum all of the S's together, your answer will also be inside, and that is wrong. So most people go into the exam room and they leave, they are happy, but the results come, they are not happy because the answers were in, but it was actually wrong, right? So please make sure you follow this. Total P is going to be 3.2 plus 3 plus 1.5 plus 2.25. That's going to give me 9.95. Okay, to find total S, we've already seen the manipulation. We know S, like we did for the first question, is P square plus Q square. That's what is going to help us. And we also know that PF, the power factor, is equal to P over S. So this is what is going to help us find our P and S, these two formulas, right? So our total S is going to be our total P square plus our total Q square. And that's going to give me 10.13, right? And my total, so unfortunately, if you have your value of S wrong, it's very likely your value of power factor will also be wrong. right? And your answer will be inside, unfortunately. So my total um, power factor is going to be total P over total S. That's 9.95 over 10.13. And that's going to be 0.98. And that's how you solve a question like this. Okay, now let's go and fill up what were what was requested from us. So the first one was to find total current. You come to that. Total kilowatts is 9.95. Total kVA is what? Total kVA is 10.13, and total power factor of the load is 0.98. So sometimes if it's objectives, you see lagging, leading, lagging, leading. So how do you know whether it's lagging? How do you know whether it's leading? Come and check your total Q. If it's negative, then the total power factor is leading. If it's positive, your total power factor is lagging. So for this one, it's going to be 0.98 leading. That is how you solve a question like this. Now, the question asks us for the total current, right? So the total current. So we know S is equal to V what times I, right? So once I know my voltage and I know my S, then I can find my I. So I will be equal to S over V. My S was given to, my total S was given to be 10.13 times 10. Remember, it is in kVA. So times 10 to the power 3 divided by my voltage was, my supply voltage was 240. 240. That's going to give me 42.2 amperes, right? And that's how you solve a question like this. Wonderful. All right, let's look at the next question. Let's look at the next question. Okay, this one says a Y connected impedance Z1 is equal to 20 plus J that, right, per phase, and is connected in parallel with a delta connected load. So if you see Y, it means a star connected load. If you see this, it means a delta connected load, right? Also 30 minus 159.3 per phase. For an impressed three-phase voltage of 415, we have line to line. Okay, you see this one expressly is mentioned is line to line. We have compute the line current A in A with its angle, then the power factor, and we are to indicate whether it's leading or lagging, and calculate the power taken by the parallel combination. So what they are saying is we have something like this, a system like this. We have another one. They are saying you have power like this. So you have a system like this, right? And this one is a balanced one, and it is all Z1. So Z1, 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 and this is Z2, 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 Z2. Right. To be able to solve a question like this, we would have to change one of them to the other. So remember, you learned something like star delta transformation, star delta, right? Star delta transformation. So you can either change from the star to, so you change all of them to all star, or you change all of them to all delta. Then the different phases will now be in parallel with each other. So when we do that, let's say I'm changing this one to a star. I'm going to have at the end of the day a system like this. Okay, where this one is Z1, Z2 star, right? I'm calling it Z2 star so that we know is the transform delta value. Then Z1 and Z2 star, then we have Z1 and Z2 star, right? So that's how it's going to look. So once it's going to be a star connected system like this, a star connected system like this. Okay. So we can, once it becomes like this, we can quickly solve it. So I'll go straight ahead. So changing from star to delta, we are dealing with a balanced load, right? So if it's delta and you are changing to a star, simply divide the value by 3. So so if I do Z2 star, it's just going to be 30.0 plus, sorry, minus J159.3 divided by 3. This is going to give me 10 minus J159.3. That's going to give me 53.1. Good. So this is going to be in parallel with per phase. So if I go for every phase, I'm going to have the Z1 value, which was 20 plus J37.75. Right. Good. And they are going to be in parallel. Now the first question was that compute was the line current A and its angle. So it's it's now star connected system, and we know V line for star connected. We know for star connected, V phase is equal to V line over root 3, right? And we know that the I, so we are saying V phase is also equal to I phase, and then I and Z, the impedance per phase, right? And we also know that I line is equal to what? I line is equal to I phase. The question is asking for the line current, right? So it means if we find I per phase, we can find the I line. That's the simple trick. I know V, I know V line, it means I can find V phase. I know Z, the impedance per phase, it means I can find what? The current per phase. Or and from that it means I can also find the line current. Right? So question, how do we find the I per phase? Right? We know we have two loads like this in parallel. So look at this. So this is going to be my phase IP and it's the same as my line current, right? I know my impressed voltage was what? 415 line to line. My V line is 415. And I know my Z per phase. So look at this. The voltage across the Z1 and Z2 are the same, and it's the same as the phase voltage, right? So you can say the current IP is going to be the sum of the current in Z1 and the current in Z2. So I'll say IZ1 plus IZ2, right? Or IZ star. But IZ1 is going to be the voltage across the, so Z1, which is the phase voltage. So VP divided by Z, the Z1 plus VP divided by the Z2 in star, right? Our VP is going to give us 415 over root 3, right? So we come and plug it in. It's going to be 415 over root 3 over root 3 divided by Z1. Z1 is what? 20 plus J 37.75. This plus 415 over root 3 divided by Z2 star is what? We found it at the top here. 10 minus 53.2. 10 minus 53.1 J. And this will give me a value of 4. Okay, so I'm computing it here. It's giving me 3.49 angle minus 9.8. Okay, so that's the current they were asking for. We know we found IP, but IP for star connected system, IP is equal to IL. So it means IL is 3.49 angle minus 9.8. Good. You see how simple it is, right? Then the next one is the power factor indicates whether leading or lagging, right? Power factor. If you know the load current and you want to find the power factor, it's just the cos of the angle for the current. So it's going to be cos 9.8, right? And this is going to give me 0.0 985, right? And then this sign should tell you whether it's leading or it's lagging. If it's a positive value, then it's leading. If it's a negative value, then it's lagging. So in this case, it's going to be what? 0.895 lagging. Is that okay? Then the next one is calculate the power taken by the parallel combination, right? The power taken by the parallel combination. So if we know, so please look at the question. It says total power P, right? Total power P. So it's P we are looking for, not S. But we know P is what? S cos theta, which is what? VL IL cos theta. So these are total power that is consumed. VL is 415, IL is 3.49, right, times cos theta. Cos theta is 0.985. That's 1427.2 watts. So someone 1.42 or 43 kilowatts. And that is your answer. Okay, right. So I'm going to start up with this question. This one says use Thevenin to find the current in the 3 ohm um, resistor. So this is the resistor we are looking for. Thevenin says I can take a whole circuit and represent it as a voltage source in series with a resistor, and the voltage source is called the Thevenin's voltage VTH, and is the open circuit voltage seen when we take out a resistor or look through a certain two terminals, right? And RTH, the Thevenin's resistance, is the resistance seen when we look into those two terminals with all sources deactivated, right? So let's go and try this question. So the first thing you do when you are solving Thevenin is that, for instance, we want to find the current in this resistor. We have to remove that resistor, and the remaining circuits, that's what we are going to be working with to find our open circuit voltage VTH and our equivalent resistance or Norton Thevenin's resistance by deactivating all sources. When we say deactivating sources, what we mean is that if there is a voltage source, short it. If there is a current source, open it, right? So you are going to start off with finding the RTH for this particular question. So this is the terminal of interest. That's where we took out our 3 ohm. Then it goes on. We finish the circuit. Right. Now over here, there's supposed to be a, a voltage source, but we short it. So the circuit looks like this, right? Then at the other side, there's also supposed to be a voltage source, right, in between these, but we short it. So we shorted out, and we have this circuit now. So here's 1, here's 5. We won't find the resistance seen from here. Here's 2, and here's 1, right? Now how do we solve this? We won't find the RTH, the equivalent resistance. We look at this, right? These two is a short circuit and a resistor, so we know this will not form part of the equivalent because it's shorted out. So we are going to have something like this, right? But it means when I look at this 1 and 2, they are in parallel and it will be in series with the 1 here. So our RTH at the end of the day will be 1 parallel 2, right, plus 1. And this is going to give us 2 over 3 plus 1. And that's 5 over 3. Right? And this, someone can say, is 1.67 ohms. Right? Okay, we found that. Then we have to find our VTH. So we bring back our sources, we draw our circuit with our sources present, right? And then here's 10 and here's 9. We have 1, 2 here, 1 here, we have 5 here, we have 1 here. So to find our open circuit voltage, we want the voltage across. If we look at these two terminals, so we have assigned the direction VTH, right? So with the direction, it means our positive is here, our negative is here. All right. Now, for this, to find our VTH, let's start and do our analysis. This is a source and it is producing a current, say I1. When it gets to this junction, this is open, so all of that current will flow through this. So we have I1 here too. The second voltage source is also producing another current. Let's call it I2. It passes through one. When it gets to this junction, here is open, so all of that will flow through this I2. It means that at the end of the day, no current is flowing through this 1 ohm resistor, so no current is flowing through that, right? We are going to write equations, KVLs around, and use that to find our VTH. So for the first loop, if I go with this loop, and I go with this loop, and I go with this loop, I can find my VTH. So the first loop, we know 10 will be equal to 5 I1. It means I1 is equal to 10 over 2, 10 over 5. That's going to give me 2 amps. What of I2? Let's go with the second loop. It means 9 is equal to I2 plus what? 2I2. It means I2 at the end of the day is equal to 9 over 3. That's giving me 3 amperes, right? Good one. Now, if you take the loop with the VTH, our VTH will be equal to 2I2, right? But there's no current in this resistor, so it will not form part of the loop. Or we can say plus 0 on 1, right? And that's going to give me 0 plus my, this will give me minus because it's going in the opposite direction to I1, so minus I5 I1, right? So it means we can find our VTH to be 2 on I2. I2 was 3, right? Minus 5 on I1 is 2. That's going to give me negative 4. Good. Negative 4 volts. What this actually tells me is that the assumed direction that I took was not, it's in the negative. So it means my real VTH is going this way. My positive is here, my minus is here, and it has a value of 4 volts, right? So when you have a question like this, especially for objectives, realize all your VTH questions will be, answers will be in positive, unless they assign the direction of VTH for you. If they assign the direction of VTH for you, then you should get their answer rightly. So assuming this question, they are the way I assumed it, that's how the question assumed it, then your answer should be -4. But if it's not giving the direction of VTH, the positive value is what we always pick. So now that we found our VTH, we are saying that we can draw the circuit to be a 4-volt source with a 5 on 3 ohm resistor, right, at the two terminals. That's what Thevenin is saying. If you now want to find the current in the resistor we took out, then we bring it back. The value was 3 ohms, and you want to find this current, right? So the current in this circuit, let's say, is I. We know I is just going to be the voltage divided by the R total. The voltage is 4 and is dividing 5/3 plus 3. Or usually people would write VTH over RTH plus the resistor that you are searching for in particular. So this is going to be 4 over 5 on 3. That's going to give me 6 over 7, or 0.857 amperes, right? Mostly when you are solving, leave them in fractions, right? You realize I use 5 over 3 and not 1.67. The answer before you approximated to get your value in the options, use that to solve, right? So I got my approximated value was 1.67, but I didn't use it to solve. I used 5 over 3. That will give me a more accurate answer in the next one that I use it in, right? So the previous answer before the approximation, use those ones for solving the next questions, right? So for this question, this is the solution. Okay, now let's take another Thevenin, right? There's one here. Sorry. Okay, let's try this next one. I think Thevenin is clear. So what you do is remove the resistor that you want the current in particular. Find your RTH by shorting all sources, right? Find your VTH, and you can find your current. Simple, very simple. All right. Now let's see this one, this question. I'll go back to my red. Okay, this question is very simple. You have to find the values of I1, I2, I3. So, but we take the opportunity to find all of them, right? It's not difficult. If you remember KCL, right? KCL says the sum of current that arrive at a node is equal to the sum of current that leaves the node. Or you can say the algebraic sum of current at a node is equal to 0, right? So for this one, we can identify several nodes, right? Several nodes. So let me give them names. I'll call this node 1, node 2, node 3, just for the sake of what we are doing. Node 4, right? If I take node 1, right, and I write the KCL for it, I'm going to say that 10 is arriving, I1 is arriving, 5 is leaving. Look at the current source. This is one of the principles you must know. If you have a current source and it's producing current, the current that leaves the source is the same current that goes back into the source. So if 5 amps is leaving here, the same 5 amps comes here. It means the current from here is 5 amps, right? So it means we are going to have 5 amps leaving plus 7 amps, which is also leaving. So at the end of the day, my I1 is going to be equal to 12 minus 10, and that is going to give me 2 amps. Then let's come to node 2. At node 2, what happens? There's also I2 leaving, I1 leaving, 5 amps coming in, 1 going out. So if you write our case here, sum of currents arriving is equal to sum of currents leaving, right? So we have 5 is arriving, all the rest are leaving. I1, which we found to be 2 amps, right, is leaving, plus 1 plus I2. It means I2 is equal to 5 minus 3. That's going to give me 2 amps again. Okay, let's go to node 3. Node 3. Node 3 is saying that at node 3 we have I2 coming in, I3 going away. Look at the current source 8. It is coming into the node. It's producing the current that is coming into the node. So we are going to say I2, which has a value of 2, plus 8 is equal to 6, which is leaving, plus I3, which is also leaving. So we are going to say I3 is equal to 10 minus 6, and that is going to give me 4 amperes, right? And then finally at node 4, we know 6 is coming in, 6, 12 is coming in, 12, right? 4 is leaving, I4, and 8 is leaving, 8. So I4 at the end of the day will be 18 minus 8, that is 10 amps. That's how you solve a question like this. Okay, very simple. Now let's look at this next one. I'll skip this one for now. Let's solve this. The question is for us to find the supply current in amps, right? So for this one, we have to analyze our circuit. Basically, what this question is demanding from you is your knowledge of short circuits and open circuits, right? Okay. For this, let's analyze and see. Between this and this, that's a short, right? So if current is coming from here, when it gets to this junction, all of the current will bypass the 6 and go into the short. So this does not form part of our circuit. Then for this one, if current is coming from here, when it gets to this point, here is open, no current to flow through this 3. When it gets to this point, all of the current to bypass the 3 and flow in the short circuit. So this does not also form our circuit. So at the end of the day, we are going to have a circuit that looks like this. This is 5, this is 10, this is I, this is 4, right? And we have 22 volts. We want to find this current I, right? For us to do that, we have to find the total resistance in the circuit. And this question has become very easy, right? So we know 5 and 4 are in parallel, right? And it will be in series with 10. So total R is what? So for parallel, let me not assume everybody knows how to do it. So it's going to be 4 times 5 over 4 plus 5, right? Plus 10. And if I want to know whether two resistors are in parallel, I just take a loop round the two resistors. If they are the only ones there, then the resistors are in parallel, right? So if I go around that loop, 4 and 5 are the only elements inside, so they are in parallel. Now it means my value is going to be 110 over 9, giving me 12.222, right? but I'm interested in finding the I. We know voltage is equal to I times the total resistance. So it means my I is going to be equal to 22 divided by the value 12.222. I told you to use 9 over 110. All right. So 22 divided by that value, giving 9.5, 9 over 5, and that's equal to 1.8. And that's the solution to that question. Right. Okay. Now let's come to another interesting subject in applied electricity. This one says use superposition to find the current Ix. Right. So if I have a circuit and there are many sources, we know that all the sources are in a way contributing some current or voltage to a particular element. Okay. Every source we have in a circuit contributes to an element voltage or current. But if we want to know the contribution of just one source to the current in that element, how do we find it? Someone brought up the superposition theorem, and we can use that for solving it. Right? So if we are going to do superposition, what we are saying is let only one source act alone. One source act alone. Right? What do you do to the other sources? We say deactivate them. Right? If it's a voltage source, you short it. If it's a current source, you open it, right? So this question will give us an illustration of opening and closing of a shorting of sources. Okay. So with this one, we are going to we are simply going to let the first part, the voltage source, act alone. So we are going to say let the 20 volts acting alone, right? It means we have to deactivate all the other sources. And if deactivating again, we are saying if it's a voltage source, short it. If it's a current source, you open it, right? So we are going to have this circuit now like this: plus, minus. Right? This is supposed to be a current source, but we know for a current source, if I want to deactivate, it means I have to open it, right? So that part opened. So we have 5 here, we have 6 here, and we have 10 here, we have 10 here, we have 20 here, right? To find our Ix, so the contribution of Ix, all right, so this is what we are saying. So this side is open, right? It means this circuit actually looks like this. Sorry. So this is really how it looks like. We want to find the current here, right? We want to current the current in this branch. So that's a contribution of the current from this source. So let's call it I1. And the current here is I2, and the current here is I1 minus I2, right? So we can take loops and then we can find our I1 and I2, and we know the current in the 6 through the 6 and 5 ohm resistor, right? So let's do that. So if we write the loop for this one and we take the loop for the bigger one, we are going to have 20 is equal to 10 I1 plus 11 I2, right? Then if we take the loop for this, is going to be 20 is equal to 10 I1 plus, sorry, this side was 4, right? So, okay, this is rather 6, this is 5, okay, it's 10, it's 10. So 10 I1 plus 10 on I1 minus I2. So in all, it's going to be 20 I1 minus 10 I2. Right. If you put that in our calculator, we are going to have our I1 to be equal to 21 over 16. That's 1.31, and I2 to be 5 over 8, and that's 0.625 amperes. So the contribution of um, the 20 volts source to the I is going to be this value, 0.25 amperes. Then the contribution of the current source, let's look at the current source acting alone. Now if you make the current source acting alone, then this will be shorted. We are going to have this this is 2 amps, this is 5 amps, this is 6 ohms, 10 ohms, another 10 ohms, right? Okay, to find the current here, right, we need to find the we need to find make this and this. We know this and this are in parallel and it's in series with this, so this we'll have to get a circuit that looks like this, 2 resistors in parallel, so that we can use current division rule to find the current we are looking for. This is 2 amps, this is 5, right? And we know 10 parallel 10, 2 resistors, 2 equal resistors in parallel will give me an effective of half of one of them. So we are going to have 5, and it's in series with 6. So we're going to have 11 here. And this is the current we are looking for. Current division rule says take the resistance in the other branch, 5, divided by their sum, 11 plus 5 times 2. This is going to give me also 0.625 amps. Great. So that's the current flowing through that one, right? So now what is the value of Ix, right? We want the value of, so we've seen the contribution of the current source, we've seen the contribution of the voltage source. So when we check the current through Ix, what is it going to be, right? So let's come back. The question has given us a direction for Ix, right? Ix is going this way. When we found the contribution of the 20 volt source, we saw it was this value, 0.625, going in the opposite direction to Ix. Ix is this way. Then for the current source, we saw that it was going this way, 0.625 amperes, right? Okay, so it means if we want to find x, ix is going to be what? The value, this one, which is going in the same direction as ix, 0.625, minus this one is going in the opposite direction. That's why you have a minus value, right? Which is 0.625. So at the end of the day, ix is actually 0 amps according to this question. It means in actual sense, no current flows through the 6 ohm resistor. Okay, so we'll end this one here as well. In the next session, we will do some more questions.